Tonight, I want you to do something simple. Hold your hands out in front of you, not too close together. Leave maybe 6 inches of space between your palms. Now look at that gap, that emptiness, that nothing, except it's not nothing. Right now, passing through that space between your hands, moving at the speed of light, are photons. Not just any photons. These are the oldest particles of light in the entire universe. They were born 13.8 billion years ago, in the first moments after the Big Bang, when the cosmos was a seething ocean of energy too hot for atoms to exist. Before we dive into this journey through the oldest light in existence, if you find this exploration fascinating, a quick like or subscribe to Space Doze really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. These ancient photons have been traveling ever since that first moment, through the formation of the first stars, through the birth of galaxies, through the slow assembly of our solar system, through every moment of human history, from the first campfires to the screen you're looking at right now. And tonight, they're passing through you. This isn't poetry. This isn't metaphor. This is physics. You are not sitting in an empty room reading or listening to these words. You are submerged in an ocean of ancient light so old that it makes the oldest stars look like newborns. This light fills every cubic centimeter of space. It passes through your walls, through your body, through your brain. Right now, as you process these words, roughly 400 photons from the birth of the universe are passing through every cubic centimeter of your body every single second. We call it the cosmic microwave background, the CMB. Scientists discovered it by accident in 1964. They thought it was noise, an error, something wrong with their equipment. What they'd actually found was the afterglow of creation itself. The faint whisper of the Big Bang, still echoing through the void. But here's what makes this discovery so deeply unsettling, so fundamentally eerie. This isn't a distant phenomenon. It's not something happening out there in some remote corner of space that we can only observe through telescopes. This is happening here, now. The cosmic microwave background isn't a photograph of the past. It's the past itself, still moving, still present, occupying the same space you occupy. You are not alone in the dark. You have never been alone. You are swimming in the ghost of the Big Bang, and you always have been. Every moment of your life, from your first breath to this exact second, you have been bathed in light that is older than the Earth, older than the sun, older than the Milky Way itself. And the strangest part? You can't see it. Your eyes weren't built to detect microwaves, but it's there, a faint glow, just 2.7 degrees above absolute zero, filling the universe like fog fills a valley. If your eyes could see in microwave wavelengths, the entire sky would glow with a soft, even light. No matter which direction you looked, day or night. That glow would be everywhere, uniform, eternal, inescapable. This is the story of that light, where it came from, what it means, and why it's still here, washing over you, carrying secrets about the universe's birth that we're only beginning to understand. Look up at the night sky. Find the Milky Way, if you can still see it through the light pollution of modern life, that band of light stretching across the darkness. Billions of stars, so many that they blur together into a river of pale luminescence. Every star you see is a ghost. Not a ghost in the supernatural sense, but a ghost in time. Light travels fast, but space is vast. The light from the nearest star, Proxima Centauri, takes 4 years to reach your eyes. You're not seeing it as it is. You're seeing it as it was 4 years ago. Look at Sirius, the brightest star in our night sky. That light left, its surface 8.5 years ago. Betelgeuse, the red giant in Orion's shoulder? That light has been traveling for roughly 700 years. It left that star around the time Marco Polo was walking the Silk Road. The Andromeda Galaxy, visible as a faint smudge if you know where to look, is 2.5 million light-years away. When that light began its journey to your eyes, humans didn't exist yet. Our Australopithecine ancestors were just beginning to walk upright in the African savanna. The farther you look into space, the deeper you look into time. Every telescope is a time machine. Every observation is archaeology. The universe doesn't give us the present. It only gives us the past, delivered at light speed, arriving like messages in bottles thrown from distant shores. But here's what astronomers realized in the 20th century. If you could somehow look far enough, deep enough, back far enough in time, you wouldn't see stars at all. You wouldn't see galaxies. You would see something else entirely. You would see the moment light itself was born. The cosmic microwave background is that moment. It's not a star that died 700 years ago. It's not a galaxy from the age before humans. It's the original ghost. The very first light that was ever free to travel through space. Before the CMB, there was no light. Not because the universe was dark, quite the opposite. The universe was so bright, so dense, so hot, that light couldn't move. Photons were trapped, bouncing between particles in an endless chaotic dance, unable to escape more than a few millimeters before colliding with something else. Then, 380,000 years after the Big Bang, something changed. The universe cooled just enough. Electrons and protons, which had been flying around as separate particles, suddenly combined to form the first neutral hydrogen atoms. And in that moment, in that cosmic instant, photons were freed. They could finally travel. They could finally move through space without being immediately absorbed or scattered. Those photons are still traveling. They've been traveling for 13.8 billion years. And tonight, some of them are traveling through you. This realization transforms everything. The ancient Milky Way stretching across your night sky is not the oldest story the universe tells. It's not even close. The oldest story is invisible to your eyes, but impossible to escape. It surrounds you, penetrates you, connects you to the first moment the universe opened its eyes and finally, for the first time, could see. Numbers become meaningless at cosmic scales. The human brain didn't evolve to grasp the vastness of geological time, let alone cosmological time. When we say the CMB is 13.8 billion years old, those words slide off the mind like water off glass. 13.8 billion. It's just a number, just syllables. So let's try something different. 1,000,000 seconds is 11.5 days. That's comprehensible. You can feel 11 days. You can remember what you were doing 11 days ago. 1,000,000 seconds ago, you were living your life, just less than 2 weeks in the past. 1,000,000,000 seconds is 31.5 years. That's a human lifetime, roughly. 1,000,000,000 seconds ago, it was 1993. The internet was just beginning. The Soviet Union had recently collapsed. The world was different, but not unrecognizably so. Now scale that up. 13.8 billion seconds is 437 years. That takes you back to the late 1500s. Shakespeare was alive, the Baroque period. Galileo was about to point his telescope at Jupiter's moons. But we're not talking about 13.8 billion seconds. We're talking about 13.8 billion years. If you wanted to count to 13.8 billion, counting one number every second without stopping, it would take you 437 years, just to count the years. And each of those years contains 31.5 million seconds. The actual age of the CMB, measured in seconds, is a number so large it would take you 13 million years just to count it. Human civilization, all of it, from the first stone tools to the smartphone in your pocket, is roughly 2.5 million years old. The CMB is 5,000 times older than that. Written language has existed for about 5,000 years. The CMB is 2.7 million times older than writing. The oldest fossils we've ever found, the first hints of life on Earth, are about 3.5 billion years old. The CMB is 4 times older than life itself. This is the light that surrounds you. This is the light passing through your body right now. Light that was already ancient when the first cell divided. Light that was already crossing the void when the first stars ignited. Light that remembers a universe so young, so small, so hot that matter as we understand it didn't yet exist. And it's still here, not as a recording, not as an echo in the metaphorical sense. It's literally, physically here. The same photons, the actual particles of light that were liberated 13.8 billion years ago when the universe first became transparent. They've been traveling ever since through the endless expansion of space, growing fainter, stretching into longer wavelengths, cooling from white-hot brilliance to a faint microwave whisper. But they never stopped moving. They never disappeared. They're here in this room, in your lungs, passing between the atoms of your skin. The question is, how did we discover them? In 1964, 2 radio astronomers at Bell Telephone Laboratories in New Jersey were trying to solve a problem that had nothing to do with cosmology. Arno Penzias and Robert Wilson were engineers, not theoretical physicists. They weren't searching for the origins of the universe. They were trying to eliminate noise from a massive radio antenna that Bell Labs wanted to use for satellite communications. The antenna itself was a remarkable piece of engineering. 20 feet tall, shaped like a giant horn, it had been built to receive signals bounced off echo balloon satellites. But by the time Penzias and Wilson started working with it, the satellite program had moved on to more advanced technology. The antenna sat idle, a monument to outdated infrastructure. Bell Labs, pragmatic as always, decided to repurpose it for radio astronomy. Penzias and Wilson were meticulous. They understood that radio astronomy required extraordinary precision. Any stray signal, any interference, any noise at all, could contaminate their observations. So they began the painstaking process of calibrating the antenna, identifying and eliminating every possible source of interference. They found plenty. Radio signals from New York City, 30 miles away. Radar from nearby airports. Electrical interference from the antenna's own equipment. One by one, they tracked down these sources and accounted for them in their calculations. But there was one signal they couldn't eliminate. It was faint, barely there. A soft hiss in the background, like the static between radio stations. At first, they assumed it was coming from the antenna itself. Perhaps a problem with the electronics. Perhaps thermal noise from some component they'd overlooked. They checked everything. They cooled the receiver to minimize thermal radiation. They tested every connection, every circuit, every wire. The hiss remained. It was constant. It never varied. It didn't matter what time of day they listened. It didn't matter which direction they pointed the antenna. They aimed it at the horizon. The hiss was there. They pointed it straight up, away from any terrestrial source. The hiss was there. They pointed it at different parts of the sky, searching for some astronomical source, a star, a nebula, a galaxy that might be producing the signal. But the signal didn't come from any particular direction. It came from everywhere, equally, uniformly, impossibly. Think about what this means for a moment. Every source of radio waves we know about has a direction. Your phone emits radio waves, but only if you're near your phone. A radio station broadcasts, but stronger in some directions than others. Even the sun, the brightest radio source in our local sky, is clearly coming from one specific location. You can point your antenna at the sun and detect it. Point away from the sun and the signal drops. But this signal had no direction. It was isotropic, the same intensity no matter where they looked. It was as if the entire sky were glowing faintly in radio wavelengths, a uniform background that filled the universe like fog. For months, Penzias and Wilson struggled with this mystery. They documented the signal carefully, measuring its properties. It had a specific temperature equivalent of about 3.5 Kelvin. They would later refine this to 2.7 Kelvin. It peaked at a wavelength of about 7.35 centimeters in the microwave part of the electromagnetic spectrum. But they had no idea what it was. They knew what it wasn't. It wasn't interference from human sources. They'd eliminated those. It wasn't coming from the antenna itself. They'd tested that exhaustively. It wasn't from any known astronomical object. They'd checked. So what was it? The answer, when it finally came, wouldn't come from their own research. It would come from 30 miles away at Princeton University, where a team of physicists had just predicted exactly this signal should exist. Before the theoretical breakthrough, before the revelation that would change cosmology forever, there were the pigeons. This is the part of the story that nobody tells in the dramatic retellings. The part where one of the most important discoveries in the history of science was almost derailed by bird droppings. 2 pigeons had taken up residence inside the horn antenna. They'd built a nest. They'd made themselves at home in this strange metal cave. And they had left behind what Penzias and Wilson, in their scientific paper, diplomatically referred to as a white dielectric material. Bird shit. The antenna was covered in bird shit. This wasn't a minor problem. At the wavelengths Penzias and Wilson were working with, even a thin coating of organic material could produce a thermal signal. The pigeons weren't just a nuisance. They were a potential explanation for the mysterious noise. Perhaps after all their careful work, after months of calibration and testing, the answer was simply that their antenna was dirty. So they cleaned it thoroughly. They removed the nest. They captured the pigeons. Gently, they were scientists, not monsters, and released them 40 kilometers away. They scrubbed every surface of the antenna, removing every trace of the white dielectric material. The pigeons came back. Somehow, across 40 kilometers of New Jersey countryside, the pigeons found their way home to the antenna. They rebuilt their nest. They resumed their residency, and Penzias and Wilson had to start over. Eventually, they solved the pigeon problem through more permanent means. The details are unclear. Some accounts suggest the pigeons were relocated even farther away. Others hint at darker solutions. What matters is that finally, definitively, the pigeons were gone. The antenna was clean. The white dielectric material was eliminated, and the hiss remained. Exactly as loud as before, exactly as uniform, exactly as mysterious. This is how science actually works. Not in clean rooms with pristine equipment and immediate revelations, but in the mess of the real world, dealing with practical problems, with pigeons and droppings and repeated failures. The universe doesn't reveal its secrets easily. It makes you work for them. It makes you eliminate every mundane explanation before you're allowed to glimpse the extraordinary truth. Penzias and Wilson had now ruled out everything. Every terrestrial source, every astronomical source, every possible contamination of their antenna. The signal was real. It was coming from space. It was coming from everywhere in space uniformly, but they still didn't know what it was. They were engineers, remember? Radio astronomers, yes, but trained in the practical arts of antenna design and signal processing. They weren't cosmologists. They weren't following the theoretical debates about the origin of the universe. They had no reason to suspect that the faint hiss they'd been trying to eliminate was actually the most important signal in cosmology. They knew they'd found something. They just didn't know what. Then, in early 1965, Penzias made a phone call to a colleague. The colleague mentioned a talk he'd attended by a physicist named Jim Peebles at Princeton. Peebles had been working with Robert Dicke, and they had a theory that predicted exactly the signal Penzias and Wilson had found. 30 miles from Bell Labs, a team of physicists at Princeton University had been developing a radical idea about the early universe. Robert Dicke, Jim Peebles, Peter Roll, and David Wilkinson were theoretical cosmologists. Unlike Penzias and Wilson, they were thinking about the Big Bang. They were following the mathematics to its logical conclusion. If the universe had begun in a hot, dense state and had been expanding and cooling ever since, there should be consequences, observable consequences. Specifically, there should be radiation left over from the hot, early universe. Thermal radiation, cooled by billions of years of cosmic expansion, but still detectable. They'd calculated what temperature this radiation should have. About 3 Kelvin, they predicted. Just a few degrees above absolute zero. And they were building an antenna to search for it. This is one of history's great ironies. While Penzias and Wilson were accidentally discovering the cosmic microwave background, Dicke's team was deliberately preparing to discover it. They were designing equipment, writing proposals, planning observations. The Nobel Prize was waiting for whoever found it first. Then Penzias called. He'd heard about Peebles' talk through the physics grapevine, the prediction of 3 Kelvin radiation filling the universe. Penzias described the signal he and Wilson had found. The 3.5 Kelvin noise that came from everywhere, that they couldn't eliminate, that had survived every test and calibration, including the removal of the pigeons. There was a pause on the line. Then Dicke called his team together. According to witnesses, his exact words were, "Boys, we've been scooped." The pieces fell into place with startling clarity. Penzias and Wilson hadn't been detecting noise. They hadn't been fighting with a malfunctioning antenna. They'd been observing the afterglow of creation itself. The cosmic microwave background. The thermal radiation left over from the Big Bang, cooled by 13.8 billion years of expansion from thousands of degrees to just 2.7 Kelvin. The theoretical prediction and the accidental observation matched perfectly. In May 1965, 2 papers were published side by side in the Astrophysical Journal. The first, by Penzias and Wilson, carefully described their observation of excess antenna temperature. The second, by Dicke, Peebles, Roll, and Wilkinson, explained what this signal meant. It was proof, not indirect evidence, not a theoretical prediction. Proof that the universe had begun in a hot, dense state. Proof that the Big Bang had actually happened. Proof that we live in a dynamic, evolving cosmos that had a beginning. The universe was not eternal and unchanging as many had believed. It had a history, an origin, and somehow, impossibly, the light from that origin was still here, still detectable, still carrying information about conditions 13.8 billion years ago. Penzias and Wilson would eventually win the Nobel Prize in Physics in 1978 for their discovery. But in 1965, standing in front of their antenna, knowing now what they'd found, I wonder what they felt. Did they look up at the sky differently? Did they feel the weight of those ancient photons passing through them? They had discovered the ghost. Now we needed to understand what the ghost was trying to tell us. To understand what Penzias and Wilson discovered, we need to go back. Not to 1964, not to the moment of their discovery, but to 380,000 years after the Big Bang, to a moment so pivotal that everything in the universe changed in an instant. But first, we need to understand what came before that moment. Imagine standing in the thickest fog you've ever experienced. Not morning mist that softens the edges of trees, not the kind of fog that makes driving cautious. Imagine fog so dense you can't see your hand in front of your face. Fog so thick that light itself can't penetrate more than a few millimeters. You're not in darkness, quite the opposite. You're surrounded by light, brilliant, blazing light. But you can't see anything because the light can't travel. It scatters and bounces and ricochets endlessly, trapped in the fog. This was the early universe. For the first 380,000 years after the Big Bang, the cosmos was opaque. Not because it was dark, but because it was too bright, too dense, too hot for light to move freely. The temperature was over 3,000 Kelvin, about half the surface temperature of the Sun. At this temperature, matter couldn't exist as atoms. It existed as plasma, a state where electrons are stripped from their nuclei, flying around independently. The universe was a sea of charged particles. Protons positively charged, electrons negatively charged, and photons, particles of light, careening between them. Here's the problem with charged particles. They interact powerfully with light. An electron and a photon cannot ignore each other. When a photon encounters a free electron, it scatters. It bounces off, changes direction, and continues until it hits another electron. And another, and another. The process is called Thomson scattering, and it made the early universe completely opaque to radiation. Think of the photons as people trying to walk through a dense crowd. You take a step, you bump into someone, you change direction. You take another step, another collision, another course correction. You're moving, but you're not getting anywhere. You're trapped in the crowd, unable to travel in a straight line for more than a moment before the next collision. This is what photons experienced in the early universe. The mean free path, the average distance a photon could travel before hitting an electron, was tiny, microscopic. A photon might move a few millimeters before scattering. In cosmic terms, it was going nowhere. The universe was filled with light, but the light was imprisoned. And this imprisonment had consequences. Because the photons kept scattering, they kept interacting with matter. Energy couldn't separate from matter. Radiation and plasma were locked together in what physicists call thermal equilibrium. The temperature of the photons and the temperature of the matter were the same. They had to be. They were constantly exchanging energy through endless collisions. This era is called the photon epoch, though that's a misleading name. It suggests the photons were in control, dominant, free. But they weren't free at all. They were trapped just as surely as the matter was trapped. Everything was coupled together. Photons, electrons, protons, in a seething, roiling, opaque plasma that filled the entire universe. If you could somehow have existed in that universe, and you couldn't, not as a biological organism, not as anything recognizable, you wouldn't see stars or galaxies or structure. You would see only an endless, uniform glow. A blazing white-hot fog pressing in from every direction. No shadows, because light didn't travel far enough to create them. No distance, because you couldn't see far enough to perceive depth. Just light, infinite and inescapable with no way out. This was the universe for 380,000 years. And then, in a moment that would echo through cosmic history, everything changed. The universe was expanding. It had been expanding since the Big Bang, and it would continue expanding forever. But expansion has a consequence. Cooling. Think of a gas canister. When you release compressed air, it gets cold. The sudden expansion drops the temperature. The universe works the same way, just on an incomprehensibly larger scale. As space itself expanded, the matter and energy within it cooled. The temperature dropped gradually, steadily, inexorably. For 380,000 years, despite this cooling, the universe remained hot enough to keep electrons and protons separate. But temperature is just the average energy of particles, and there's a threshold where electrons can no longer resist the electromagnetic attraction of protons. That threshold is around 3,000 Kelvin. When the universe cooled below this critical temperature, something remarkable happened. Electrons and protons began to stick together. They formed the first neutral atoms. This process is called recombination, though it's a misleading term. The prefix "re" suggests it happened before, that electrons and protons were recombining, getting back together. But this was the first time. Before this moment, atoms had never existed. The name stuck anyway, inherited from laboratory physics where recombination usually means ions and electrons reuniting. Hydrogen was first. A single proton capturing a single electron, forming the simplest atom in the periodic table. This wasn't instantaneous. It happened gradually across thousands of years as the temperature dropped through the critical threshold. But in cosmic terms, thousands of years is instantaneous. The universe is 13.8 billion years old. A few thousand years is a blink. As more and more electrons bound to protons, the number of free electrons in space plummeted. And this changed everything for the photons. Remember, photons scatter off charged particles. Free electrons are charged, but neutral hydrogen atoms are not. An atom has a positive nucleus and negative electrons, but the charges cancel out. The net charge is zero. And photons mostly ignore neutral atoms. They can pass right through them without scattering. So as recombination proceeded, as free electrons disappeared into atoms, the opacity of the universe dropped. The fog began to clear. Not gradually, but suddenly, like someone flipping a switch. The mean free path of photons, the distance they could travel before scattering, had been millimeters. Now, suddenly, it was infinite. A photon could cross the entire universe without hitting anything. Light was free. For the first time since the Big Bang, photons could move in straight lines. They could travel. They could escape from the region where they were created and journey across space. The universe, which had been opaque for 380,000 years, became transparent in what amounts to a cosmic instant. This is the moment captured in the cosmic microwave background. The CMB isn't showing us the Big Bang itself. That moment remains hidden behind the opaque fog of the photon epoch. What the CMB shows us is this moment, the moment of recombination. The last time these photons interacted with matter before beginning their 13.8 billion year journey through space. It's sometimes called the surface of last scattering. The photons were scattered one final time by electrons in the plasma, and then they were free. That final scattering imprinted a pattern on the light, tiny temperature variations that reflected density variations in the plasma. And those photons have been traveling ever since, carrying that pattern like a message in a bottle, like a photograph of the universe as it was 380,000 years after its birth. Here's what makes this moment so profound, so cosmically significant. Before recombination, the universe had no structure. It couldn't. The photons and matter were coupled together in thermal equilibrium. Any region that tried to collapse under its own gravity would be immediately pushed back apart by photon pressure. Light was pushing on matter, preventing it from clumping, keeping everything smooth. Think of it like trying to compress air with your hands. Push it together and it pushes back. The pressure resists compression. In the early universe, photon pressure was immense, overwhelming, preventing any gravitational collapse. But when recombination happened, when the photons decoupled from matter, that pressure suddenly vanished. Matter was free to respond to gravity without photon pressure fighting back. Regions that were slightly denser than average could finally begin to collapse. The seeds of structure, galaxies, stars, planets, us, could finally begin to grow. The cosmic microwave background marks this transition. It's the last moment of the smooth, homogeneous universe. After this, structure formation could begin. Gravity could start pulling matter together. The universe could become interesting. But there's something else, something that makes this moment uniquely special in cosmic history. The photons released at recombination have been traveling ever since. They haven't interacted with anything. Oh, space itself has expanded, stretching their wavelengths from visible light to microwaves. And occasionally, one might be absorbed by dust or gas. But for the most part, these photons have traveled freely through 13.8 billion years of cosmic history without being touched. This means they carry information. Pure, uncontaminated information about what the universe was like 380,000 years after the Big Bang. The tiny temperature variations in the CMB, those 1 part in 100,000 fluctuations that satellites have mapped with such precision, are a direct measurement of density variations in the primordial plasma. No other observation in astronomy gives us information this direct, this ancient, this pure. When we look at distant galaxies, we're seeing them as they were billions of years ago, yes, but we're seeing light that was emitted by stars, processed through stellar atmospheres, potentially absorbed and re-emitted by dust, affected by the matter between the galaxy and us. It's not pristine information. The CMB is pristine. It's the oldest light possible to observe. There is nothing older because before recombination, the universe was opaque. You cannot see past the surface of last scattering any more than you can see into the sun's interior. The light doesn't escape. So the CMB is a wall, a boundary, the farthest we can see into the past using light. But it's not a wall that blocks our view. It's a wall that shows us something. A photograph of the universe in its infancy, encoded in the pattern of photons that filled space when atoms first formed. And those photons are still here. They didn't arrive at Earth and stop. They're everywhere, filling all of space uniformly because they were released everywhere uniformly. Every cubic centimeter of the universe contains about 400 CMB photons at any given moment. They pass through that space at the speed of light, replaced immediately by new ones arriving from other directions, creating a constant, uniform bath of ancient radiation. You are immersed in this. Right now, the past isn't behind you. It's passing through you, moving at the speed of light, on its eternal journey through the cosmos. When those photons were released at recombination, they weren't microwaves. They were visible light, orange-red specifically. The temperature of 3000 Kelvin produces light with a peak wavelength in the visible spectrum, similar to the glow of heated metal or the filament in an old incandescent bulb. If you could have witnessed recombination, if you could have been there in that impossible moment, the universe would have looked like the inside of a furnace. A uniform orange glow filling all of space, gradually fading as the temperature dropped, shifting from bright orange to dim red to infrared, and finally becoming invisible as it cooled below the threshold where thermal radiation produces visible light. But something else was happening while the light cooled. Something far more dramatic. Space itself was expanding. This is the hardest concept in cosmology to grasp intuitively. We think of space as a stage, a fixed arena where things happen. Objects move through space. Light travels through space. But space itself is static, unchanging, just there. Except it's not. Space is dynamic. It can expand, and it has been expanding since the Big Bang. When we say the universe is expanding, we don't mean galaxies are flying apart through space like debris from an explosion. We mean space itself is stretching. The distance between any 2 points that aren't gravitationally bound together is increasing because new space is being created between them. This has a profound effect on light traveling through that space. Imagine drawing a wave on a rubber sheet, a sine wave with a specific wavelength, the distance between peaks. Now stretch the rubber sheet. The wave stretches too. The wavelength increases. The peaks spread apart. If you stretch the sheet enough, a wave that started with a wavelength of 1 centimeter might end up with a wavelength of 1 meter, or 10 meters, or 1,000 meters. This is what's happening to the photons from the CMB. They were released with wavelengths around 1,000 nanometers, the near-infrared part of the spectrum. But they've been traveling through expanding space for 13.8 billion years. During that journey, space has expanded by a factor of about 1 to 100. The universe today is 1,100 times larger than it was at recombination. And the wavelengths of those photons have stretched by the same factor. 1,000 nanometers multiplied by 1,100 equals 1.1 millimeters. That's in the microwave part of the electromagnetic spectrum, right where Penzias and Wilson detected it. The stretching of space has shifted the light from the orange-red of heated metal to the invisible microwaves your kitchen appliance uses to heat food. This stretching is called cosmological redshift. The name comes from visible light, where stretching wavelengths shifts light toward the red end of the spectrum. Stretch it further, and it becomes infrared, invisible to human eyes. Stretch it even more, and it becomes microwave radiation. Redshift is how we measure cosmic distance and time. When astronomers observe a distant galaxy, they measure how much its light has been redshifted. The amount of redshift tells them how much the universe has expanded since that light was emitted, which tells them how long ago it was emitted, which tells them how far away the galaxy is. The CMB has a redshift of about 1 to 100. That's the highest redshift we can ever observe using light, because before recombination, the universe was opaque. The CMB marks the boundary, the cosmic horizon beyond which light cannot reach us. But here's what makes this truly eerie. The redshift isn't over, it's still happening. Right now, as those ancient photons pass through you, they're being stretched. The wavelength is increasing, the temperature is dropping. The CMB is very slightly colder today than it was yesterday, and it will be very slightly colder tomorrow than it is today. The change is immeasurably small on human timescales, but it's real. The universe is still expanding. The photons are still stretching. The ghost of the Big Bang is slowly fading, cooling, becoming harder to detect with each passing eon. Here's a puzzle that confuses almost everyone when they first encounter it. The universe is 13.8 billion years old. Light travels at a finite speed, about 300,000 kilometers per second, or about 186,000 miles per second. So the farthest we should be able to see is 13.8 billion light years in any direction, right? Light from farther away hasn't had time to reach us yet. That would make the observable universe a sphere 27.6 billion light years across. That's already incomprehensibly vast, but it seems logical. Except it's wrong. The observable universe is actually much larger, about 93 billion light years across, a sphere 46.5 billion light years in radius. How is this possible? How can we see light from objects more than 13.8 billion light-years away when the universe is only 13.8 billion years old? The answer is expansion. When we observe a photon from the CMB, that photon has been traveling for 13.8 billion years, yes. But the location where it was emitted, that patch of space at the surface of last scattering, hasn't stayed 13.8 billion light-years away. It's been moving away from us because space itself is expanding. Think of it this way. Imagine you're standing on a long rubber sheet that's being stretched. Someone throws a ball toward you from far away. The ball is moving toward you at a constant speed, but while it's traveling, the rubber sheet is stretching, carrying the thrower farther away. By the time the ball reaches you, the thrower is much farther away than they were when they threw it. That's what's happening with CMB photons. They were emitted from a region that was much closer to us than 46.5 billion light-years. In fact, when recombination happened, the region we now observe as the farthest edge of the CMB was only about 42 million light-years away from our location. That's the distance light could travel in the first 380,000 years. But during the 13.8 billion years those photons were traveling toward us, space was expanding. The location that emitted them was being carried away by expansion even as its light was traveling toward us. It's like running on a treadmill that's accelerating faster than you can run. You're moving forward, but you're also being carried backward, so your net progress is less than your speed would suggest. By now, that location has been carried to about 46.5 billion light-years away. That's the current distance to the surface of last scattering, and there's a symmetric sphere in all directions, which is why the observable universe is about 93 billion light-years across. This has a profound implication. The photons we detect from the CMB today were emitted from locations that are now far beyond what we can ever observe. If we could somehow take a photograph of the universe as it exists right now, if we could freeze time and see the current state of everything simultaneously, we would see that the regions that emitted the CMB photons reaching us today are regions we will never see as they currently are. We're seeing the past of regions that have become unreachable. The CMB is a message from places that no longer exist in our observable universe, from regions that have been carried beyond our cosmic horizon by the relentless expansion of space. This brings us to one of the most unsettling realizations in cosmology. The observable universe is only a fraction of the total universe. We can only see as far as light has been able to travel since the Big Bang, accounting for expansion. That's our cosmic horizon. Beyond that horizon are regions of space we cannot observe, cannot measure, cannot know anything about through any form of light or radiation. And the universe beyond that horizon might be infinite. Think about what this means. The 93 billion light-year diameter sphere we can observe might be an infinitesimally small fraction of everything that exists. If the universe is infinite, and current evidence suggests it might be, then the observable universe is literally 0% of the total universe. An infinite cosmos extends beyond our horizon in all directions, filled with galaxies and stars and planets we will never see. Those regions have their own CMB photons, their own surface of last scattering, their own patch of the primordial universe that became transparent 13.8 billion years ago. But we will never detect those photons. They're traveling through space, just like the ones passing through us, but they're traveling in directions that will never intersect our location. And here's where it gets stranger. The cosmic horizon is not fixed. It's growing as time passes, and light from more distant regions has time to reach us. Every day, our observable universe gets slightly larger. New galaxies come into view at the edge of our cosmic horizon, regions we couldn't see yesterday but can see today. But Expansion is accelerating. Dark energy, a mysterious force we'll discuss later, is pushing space apart faster and faster. Eventually, the acceleration will be so strong that new regions will be carried away from us faster than light from those regions can reach us. The cosmic horizon will stop growing. It might even shrink. In the far future, billions of years from now, galaxies that we can see today will be redshifted beyond visibility. They'll cross our cosmic horizon, receding faster than light, and their light will never reach us again. The observable universe will shrink, not because the universe is contracting, but because expansion is accelerating so rapidly that light from distant regions can no longer keep up. This means the CMB itself has a horizon. There are CMB photons that will never reach us. They're out there traveling through space, carrying information about the primordial universe, but they're in regions of space that are receding from us so fast that their light cannot catch up. And it works both ways. The CMB photons passing through your body right now will continue traveling after they leave. They'll cross light years, millions of light years, billions of light years of space. Some will eventually reach regions of the universe we can never observe. Beings in those distant regions, if they exist, will someday detect these photons. They'll see them as part of their cosmic microwave background, a uniform glow filling their sky, just as we see ours. The CMB is not just our ancient light, it's everyone's ancient light. Every observer in the universe, no matter where they are, sees their own CMB surrounding them, filling their sky, washing over them with photons from the moment their local universe became transparent. We are all immersed in the same ghost, each of us seeing our own portion of its infinite expanse. When the Doze satellite, the Cosmic Background Explorer, first mapped the entire sky in microwave wavelengths in the early 1990s, scientists discovered something that was simultaneously expected and deeply mysterious. The cosmic microwave background was almost perfectly uniform. Almost. If the CMB were perfectly uniform, if every direction in the sky had exactly the same temperature, the universe would be featureless. There would be no structure, no galaxies, no stars, no planets, no us. A perfectly smooth universe would remain perfectly smooth forever. Gravity needs something to work with, a slight overdensity here, a slight underdensity there, to begin pulling matter together. So scientists knew there had to be variations, tiny imperfections in the primordial plasma, seeds that gravity could amplify over billions of years into the cosmic web of galaxies we see today. But they didn't know how large these variations would be, or if instruments sensitive enough to detect them could even be built. When Doze data came back, the variations were there. Temperature differences across the sky, some regions slightly hotter than average, some regions slightly cooler, but the differences were incredibly small. 1 part in 100,000. Think about what this means. If the average temperature of the CMB is 2.725 Kelvin, the variations are only about 3 Kelvin, 30 microkelvins. If you took two regions of sky separated by a significant angle and measured their temperatures, they might differ by 300,000ths of a degree. This is why it took until the 1990s to detect these fluctuations, even though physicists had predicted their existence decades earlier. The technology simply didn't exist to measure temperature differences this small across the entire sky. Doze was a triumph of precision engineering, able to detect variations so subtle they were almost lost in the noise. But these tiny variations were everything. George Smoot, one of Doze's principal investigators, famously said when the results came in, "If you're religious, it's like looking at God." What he meant was that these fluctuations were the blueprint of creation, the pattern from which everything would emerge, Every galaxy, every star, every atom in your body can trace its lineage back to these tiny temperature variations in the primordial plasma. The pattern wasn't random, it had structure, statistical properties. When you analyze the fluctuations mathematically, breaking them down by angular scale, how big the hot and cold spots were, you found peaks at specific scales. These peaks told a story about what was happening in the plasma before recombination. Later, satellites refined these measurements. MAP, the Wilkinson Microwave Anisotropy Probe, launched in 2001 and observed for 9 years, producing maps of exquisite detail. Then Planck, the European Space Agency's mission, launched in 2009 and observed until 2013, creating the most precise map of the CMB we've ever had. These maps are color-coded for temperature. Red regions are slightly warmer than average. Blue regions are slightly cooler. When you look at these maps, and you can find them online, false-colored and beautiful, you're looking at the universe as it was 380,000 years after the Big Bang. You're seeing structure that existed before the first stars formed, before galaxies assembled, before anything recognizable came into being. And you're seeing your own origin story. The particular fluctuation pattern in our region of the universe determined where galaxies would form, which galaxies would be large, which would be small, where the Milky Way would eventually assemble, where our solar system would form within it. The exact pattern of temperature variations in our patch of the primordial sky determined the entire future history of our cosmic neighborhood. Those variations look random at first glance, chaotic splotches of red and blue scattered across the sky. But there's order hidden in the chaos, a pattern waiting to be decoded. The pattern in the CMB fluctuations comes from sound. This sounds absurd at first. Sound in space? Everyone knows space is a vacuum. Sound needs a medium, air, water, something physical for pressure waves to travel through. Space is empty. Sound cannot exist in space. But the early universe wasn't a vacuum. It was a dense plasma of particles. And in that plasma, sound waves could propagate just like sound propagates through air or water. Here's how it worked. The very early universe, before recombination, when everything was still plasma, had regions that were slightly denser than average. These overdensities were probably created by quantum fluctuations during inflation, stretched to cosmic scales by the exponential expansion. They were tiny variations in density, but they were real. An overdense region has more matter. More matter means stronger gravity. Gravity tries to pull the region together, making it collapse inward and become even denser. But the plasma contains photons, lots of photons, and photons create pressure. As the region tries to collapse under gravity, photon pressure pushes back, resisting the compression. The region compresses, pressure builds, and then the region bounces back, expanding outward. Then gravity pulls it back in again. Compress, expand, compress, expand. The region oscillates. It bounces back and forth, driven by the competition between gravity trying to compress it and photon pressure trying to expand it. This is a sound wave, a pressure wave propagating through the plasma. Regions of compression and rarefaction moving outward from the initial overdensity at the speed of sound in the plasma, which was about 60% the speed of light, incredibly fast by everyday standards, but still slower than light itself. These sound waves were real physical oscillations in the primordial plasma. Compression waves traveling outward from density perturbations, bouncing back and forth between gravity and pressure. They're called baryon acoustic oscillations, baryon being the term for normal matter made of protons and neutrons. The sound waves propagated for 380,000 years. That's how long the universe remained a plasma, with photons and matter coupled together. During those 380,000 years, the sound waves traveled outward from each initial density perturbation, creating shells of compressed and rarefied plasma. Then recombination happened. Suddenly, the photons decoupled from matter. Photon pressure vanished. The sound waves froze. Whatever pattern existed at that moment, whatever distribution of compressed and rarefied regions, became fixed in place. The music stopped, and the pattern of oscillations was locked into the distribution of matter. That frozen pattern is what we see in the CMB temperature fluctuations. Hot spots correspond to regions that were compressed when the music stopped. Cold spots correspond to rarefied regions. The size of the spots tells us how far sound waves traveled in 380,000 years, a distance now called the sound horizon. And here's the remarkable part. That same pattern, frozen into the matter distribution at recombination, still exists today. The overdensities created by sound waves in the primordial plasma became the seeds where galaxies would eventually form. When you map the distribution of galaxies across the modern universe, you can still see the imprint of those ancient sound waves. A slight excess of galaxies separated by about 500 million light-years, the distance that sound traveled in the first 380,000 years, stretched by 13.8 billion years of expansion. The universe still remembers the sound of its birth. These fluctuations, these tiny temperature variations, these frozen sound waves, were the seeds from which everything grew. After recombination, after photons decoupled from matter, gravity could finally work unimpeded. Regions that were slightly overdense began pulling in more matter, slowly at first. Gradually, over millions of years, the overdensities grew. Matter flowed along gravitational gradients like water flowing downhill. Denser regions became denser. Less dense regions became emptier as their matter was pulled away toward the overdensities. The smooth universe began developing structure. The first stars formed about 100 to 200 million years after the Big Bang, igniting in the densest regions where gas had collapsed under gravity. These were massive, hot, short-lived stars made purely of hydrogen and helium. No heavier elements existed yet. When they exploded as supernovae, they scattered heavier elements into space, enriching the gas from which the next generation of stars would form. Galaxies assembled from collections of these early stars, pulled together by gravity into rotating systems. Small galaxies merged into larger ones. Dark matter, which we'll discuss in the next section, provided additional gravitational scaffolding, creating deep, potential wells where normal matter could collect. Over billions of years, the structure we see today emerged. Galaxy clusters. Filaments of galaxies stretching across hundreds of millions of light years. Vast voids nearly empty of galaxies. The cosmic web, a sponge-like structure of matter separated by emptiness. All of it traces back to those 1 part in 100,000 fluctuations in the CMB. If the fluctuations had been larger, say 1 part in 10,000, structure would have formed more quickly and more violently. The universe might be dominated by massive black holes, with few galaxies able to survive. If the fluctuations had been smaller, 1 part in a million, structure formation would have been too slow. Galaxies might not have formed at all, or only very recently, leaving no time for stars and planets and life to develop. The amplitude of the fluctuations had to be just right. And it was. 1 part in 100,000 was exactly the right size for gravity to work with, over billion of years amplifying tiny variations into the rich structure we observe. Scientists can run computer simulations starting from the fluctuation pattern observed in the CMB. They input the initial conditions, the exact pattern of overdensities and underdensities from the surface of last scattering. Then they let gravity and physics evolve the simulation forward through billions of years of cosmic time. The results match reality with stunning precision. The simulated universe develops galaxies, clusters, filaments, and voids that look remarkably like what we observe through telescopes. The match isn't perfect. There are still mysteries and discrepancies, but it's close enough to confirm that we understand the basic story. The structure of the universe today, the distribution of galaxies, the location of the Milky Way, the formation of our solar system, your existence. All of it was encoded in the pattern of temperature fluctuations visible in the cosmic microwave background. 13.8 billion years ago. You are made from quantum fluctuations, stretched to cosmic scales, evolved through gravity, assembled into stars and planets, and eventually, impossibly, into consciousness. There's something else in those CMB fluctuations, something invisible, something that doesn't show up in the temperature map directly, but leaves its fingerprints in the pattern. Something that was already there, already clumping, already building structure while normal matter was still trapped in the plasma. Dark matter. We've known about dark matter since the 1930s, when astronomer Fritz Zwicky observed galaxy clusters and noticed something impossible. The galaxies were moving too fast. They were orbiting within the cluster at speeds that should have torn the cluster apart. The visible matter, all the stars and gas he could observe, didn't have enough gravity to hold them together. There had to be something else. Something with mass. Something creating gravity. Something completely invisible. He called it dark matter, and for decades most astronomers dismissed the idea. Maybe Zwicky had measured the velocities wrong. Maybe Newton's laws of gravity didn't work quite right at such large scales. Then in the 1970s, astronomer Vera Rubin measured the rotation curves of spiral galaxies. She observed how fast stars orbit at different distances from the galactic center. According to Newton and Einstein, stars farther from the center should orbit more slowly, just like planets farther from the sun orbit more slowly. But that's not what Rubin found. Stars at the edge of galaxies were orbiting just as fast as stars closer to the center. The rotation curves were flat, not declining. This made no sense unless there was additional mass in galaxies that we couldn't see. A lot of additional mass. Roughly 5 times more mass than all the visible stars and gas combined. The evidence kept accumulating. Gravitational lensing showed that galaxy clusters contain far more mass than their visible matter suggests. The cosmic microwave background fluctuations had features that could only be explained if dark matter was present in the early universe. Simulations of galaxy formation failed unless you included dark matter as a major component. Today, the evidence is overwhelming. Dark matter exists. It makes up about 27% of the universe's total energy content, compared to only 5% for normal matter. For every kilogram of normal matter in the universe, there are roughly 5 kilograms of dark matter. But here's what makes dark matter so crucial for understanding the CMB and structure formation. Dark matter doesn't interact with photons. It doesn't scatter light. It doesn't absorb or emit radiation. The only way dark matter interacts with anything is through gravity. This means that during the photon epoch, when normal matter was trapped in plasma, coupled to photons through electromagnetic interactions, dark matter was already free. It wasn't coupled to anything except gravity. It could clump, it could collapse, it could begin forming structure. While normal matter was being pushed around by photon pressure, resisting gravitational collapse, dark matter was quietly building the framework of the cosmic web. It was collapsing into filaments and nodes, creating gravitational wells, constructing the invisible scaffolding upon which galaxies would eventually form. Think of it like building a house. Dark matter created the framework, the skeleton, the invisible structure. Normal matter, once it was finally freed at recombination, flowed along that framework like water filling a mold. It followed the gravitational valleys carved by dark matter, collecting in the deepest potential wells, forming the visible galaxies we see today. Without dark matter, structure formation would have taken far longer. The tiny fluctuations in normal matter, those 1 part in 100,000 variations, would have grown slowly under gravity alone. Galaxies might not have formed until very recently in cosmic history, if at all. There wouldn't have been time for stars to form, for heavy elements to be forged in supernovae, for planets to assemble, for life to evolve. Dark matter accelerated structure formation by providing additional gravity. Its presence amplified the growth of fluctuations, allowing structure to form on timescales that made our existence possible. The most dramatic evidence for dark matter comes from a cosmic collision that happened 3.8 billion light-years away. Two galaxy clusters smashed into each other at speeds of millions of kilometers per hour. This wasn't a recent event. It happened about 150 million years ago, and we're only seeing it now because light takes that long to travel the distance. But when astronomers observed the aftermath with multiple telescopes, they found something extraordinary. This collision is called the bullet cluster, named for the bullet-shaped cloud of hot gas visible in X-ray images. And it provides perhaps the clearest evidence we have that dark matter is real. Here's what happened. Galaxy clusters are mostly empty space. The galaxies themselves are tiny compared to the distances between them. When two clusters collide, the galaxies mostly pass through each other without direct impacts. But galaxy clusters also contain enormous amounts of hot gas between the galaxies, the intracluster medium. Unlike galaxies, gas clouds do interact when they collide. The hot gas from one cluster slams into the hot gas from the other cluster at tremendous speeds. The collision heats the gas even further, to tens of millions of degrees, making it glow brightly in X-rays. The gas is slowed by the impact, remaining near the collision site while the galaxies continue moving forward. When astronomers mapped the mass distribution in the bullet cluster using gravitational lensing, measuring how the cluster bends light from background galaxies, they found something remarkable. Most of the mass wasn't where the hot gas was. Most of the mass was where the galaxies were, having passed straight through the collision. This is exactly what you'd expect if dark matter exists. The galaxies are embedded in massive halos of dark matter. When the clusters collided, the dark matter halos, like the galaxies themselves, passed through each other because dark matter doesn't interact with itself, except through gravity. The dark matter kept moving forward, but the gas, which interacts electromagnetically, collided and stopped. So the visible matter, the gas glowing in X-rays, is in one location, but the mass, detected through gravitational lensing, is in a completely different location, having passed beyond the collision site. The mass distribution doesn't match the visible matter distribution. This is devastating to theories that try to explain galaxy rotation curves by modifying gravity rather than invoking dark matter. If you modified gravity to be stronger at large distances, you'd expect the gravitational effects to be centered on the visible matter. But in the bullet cluster, the gravitational effects are clearly separated from most of the visible matter. Dark matter behaves like matter. It has mass, it creates gravity, and it can pass through other matter like a ghost. It just doesn't interact electromagnetically, making it invisible to light. The bullet cluster isn't an isolated case. Astronomers have found other colliding clusters showing the same separation between visible matter and gravitational mass. Each one reinforces the reality of dark matter. Each one shows that the universe contains vast quantities of invisible matter that we detect only through its gravitational influence. Let's bring this back to the CMB. and what it tells us about dark matter in the early universe. When scientists analyze the CMB fluctuation pattern, the peaks in the angular power spectrum, the statistical properties of hot and cold spots, they can extract information about how much normal matter and how much dark matter existed at recombination. The ratio is about 5:1. For every kilogram of normal matter, protons, neutrons, electrons, the stuff that makes atoms, there were about 5 kilograms of dark matter. This ratio has been confirmed by multiple independent methods. Galaxy rotation curves give the same ratio. Galaxy cluster dynamics give the same ratio. Gravitational lensing studies give the same ratio. The formation of large-scale structure only works in simulations if you use this ratio. The universe is dominated by invisible matter. Normal matter, everything you can see and touch, everything made of atoms, is a minority component. We live in a dark matter universe with a thin frosting of normal matter on top. And this has profound implications for how the CMB formed and how structure grew from it. The fluctuations we see in the CMB temperature map represent variations in normal matter. The plasma of protons and electrons that scattered the photons one last time before recombination. But beneath that pattern, invisible in the CMB directly, was the dark matter distribution. Dark matter had already formed deeper potential wells than normal matter could. While normal matter was being pushed around by photon pressure, creating sound waves that oscillated and froze at recombination, dark matter was collapsing unimpeded. It was building structure more aggressively, creating gravitational wells that would later pull in the normal matter once photons could no longer resist. Some scientists describe dark matter as the gravitational scaffolding of the universe. It created the framework. Normal matter decorated that framework with light, stars and galaxies that we can actually observe. But the framework itself, the underlying structure, is dark matter. This is why simulations of structure formation require dark matter. If you try to simulate galaxy formation using only normal matter, starting from the CMB fluctuation pattern, you don't get the universe we observe. Galaxies form too slowly. The cosmic web doesn't develop the right structure, but add dark matter in the right proportion, that 5:1 ratio, and everything works. Galaxies form. At the right times, they have the right masses. The cosmic web develops the correct filamentary structure. The simulations match reality. We still don't know what dark matter is made of. Despite decades of experiments searching for dark matter particles, we haven't detected them directly. We know dark matter exists because we see its gravitational effects everywhere we look, but its fundamental nature remains mysterious. What we do know is that dark matter shaped the universe from the earliest moments. It was there in the plasma before recombination, creating the invisible scaffolding. It amplified the tiny fluctuations visible in the CMB, accelerating structure formation. And it continues to dominate the gravitational landscape of the universe today, holding galaxies together, shaping the cosmic web, making our existence possible. 5 kilograms of mystery for every kilogram of reality. There's a puzzle hidden in the cosmic microwave background. A puzzle so profound that it nearly broke cosmology in the 1970s before a radical solution was proposed. The puzzle is this: the CMB is too uniform. That sounds backwards, doesn't it? We just spent an entire section discussing the tiny variations in the CMB, the 1 part in 100,000 fluctuations that seeded all structure. But zoom out from those fluctuations and look at the average temperature. Look at the CMB from opposite sides of the sky, regions separated by the entire observable universe. They have the same temperature, exactly the same to within 1 part in 100,000. Why is this a problem? because those regions have never been in contact. They've never communicated. Light from one region hasn't had time to reach the other region, not even in 13.8 billion years. They are, and have always been, beyond each other's cosmic horizons. Think about what temperature means. Temperature is a measure of how much energy particles have, how fast they're moving. For two regions to have the same temperature, they need to have exchanged energy. They need to have reached thermal equilibrium. But the universe isn't in contact with itself. When we look at the CMB, we're seeing light from 13.8 billion years ago that's been traveling toward us ever since. The farthest edge of the CMB we can see is about 46.5 billion light-years away now, accounting for expansion. But there's CMB in the opposite direction too, also 46.5 billion light-years away. Those two edges are separated by 93 billion light-years. Light from one edge would need 93 billion years to reach the other edge. But the universe is only 13.8 billion years old. So how do these causally disconnected regions know to have the same temperature? It's as if you walked into two completely separate rooms, rooms that have never been connected, rooms that have been isolated since they were built, and found they both have exactly the same temperature, humidity, and air pressure, down to infinitesimal precision, not approximately the same, exactly the same. That would be strange. It would demand an explanation. The early universe has about 1 million such regions visible in our CMB map. 1 million separate patches that should have had no way to coordinate with each other. No way to smooth out temperature differences. No way to reach equilibrium. And yet, they did. This is called the horizon problem. Regions beyond each other's causal horizons shouldn't be able to coordinate their properties. But somehow, the universe achieved remarkable uniformity despite being composed of disconnected regions that couldn't communicate. For years, this was simply accepted as an initial condition. Maybe the universe just started out uniform for reasons we didn't understand. Maybe that was simply how the Big Bang worked. But that's not satisfying. Science works by finding explanations, not accepting mysteries as brute facts. If the universe appears fine-tuned, if it started with precisely the right conditions to produce what we observe, then there should be a mechanism explaining how those conditions arose. In 1980, a physicist named Alan Guth proposed a solution so radical, so extreme, that it seemed almost absurd. What if the universe didn't start out disconnected? What if all those regions we see in the CMB, all those patches separated by billions of light years today, were once close together? Close enough to reach thermal equilibrium, close enough to communicate and coordinate their properties. And then something happened, something violent, something that stretched space itself exponentially, faster than light, inflating a tiny region to cosmic scales in a fraction of a second. Inflation. Imagine taking a balloon and drawing dots all over its surface. The dots represent different regions of the early universe. When the balloon is deflated, the dots are close together. They can interact. They can exchange heat and reach the same temperature. Now inflate the balloon, rapidly, exponentially. In seconds, the balloon grows from the size of a marble to larger than the observable universe. The dots are now separated by vast distances. They're beyond each other's horizons. They can no longer communicate. But they still have the same temperature because they were in contact before the inflation. They reached equilibrium when they were close together, and inflation preserved that equilibrium even as it stretched them to cosmic scales. This is the core idea of cosmic inflation. Before the hot Big Bang that created the plasma and eventually the CMB, there was a brief period of exponential expansion. a moment when space itself expanded faster than light, doubling in size again and again in tiny fractions of a second. The numbers are staggering. In perhaps 10 or 36 seconds, a decimal point followed by 35 zeros before you reach the 1, the universe expanded by a factor of at least 10 to 26. A region smaller than a proton inflated to larger than a grapefruit, possibly much larger. This solves the horizon problem elegantly. All the regions we see in the CMB were once part of a tiny patch of space, much smaller than an atom, small enough that light could cross it instantaneously. That patch reached thermal equilibrium before inflation. Then inflation stretched it to cosmic scales, creating what we now see as causally disconnected regions that nonetheless share identical properties. Inflation also solves the flatness problem. The universe appears to be spatially flat. Parallel lines stay parallel forever, but flatness is unstable. Any slight curvature in the early universe should have grown dramatically over time, unless inflation happened. Inflating a curved surface makes it flatter. The surface of an uninflated balloon is obviously curved, but inflate it to enormous size and any small patch appears flat. Inflate space by a factor of 10 to the 26 or more and any initial curvature becomes negligible. But inflation does something else. Something profound, something that brings us back to those tiny fluctuations in the CMB. During inflation, quantum mechanics was operating. And quantum mechanics says that fields fluctuate randomly at the smallest scales. These quantum fluctuations are normally microscopic, irrelevant to anything we can observe. But during inflation, space was expanding so rapidly that quantum fluctuations were stretched to macroscopic scales. Think of it like this. A quantum fluctuation appears at the subatomic scale. Before it can disappear, inflation grabs it and stretches it. The fluctuation grows from smaller than a proton to larger than a galaxy. It becomes frozen into the fabric of space itself. These inflated quantum fluctuations became the density variations we see in the CMB. The 1 part in 100,000 temperature differences across the sky originated as quantum uncertainties in the inflation field. The smallest possible variations allowed by quantum mechanics stretched to the largest scales in the universe. The CMB fluctuations are quantum mechanics writ large. They're the fingerprint of inflation. And if we look carefully enough, we might find an even more direct signature. A signature written not in density variations, but in the twisting of light itself. A signature that would prove inflation happened and tell us exactly how violent that first moment was. Inflation didn't just create density fluctuations. It should have created gravitational waves. During inflation, space itself was rippling, not just expanding uniformly, but vibrating with quantum fluctuations in the gravitational field itself. These fluctuations in space-time would propagate outward as gravitational waves. These primordial gravitational waves would be completely different from the gravitational waves LIGO detects from colliding black holes. Those waves are recent, local. Primordial gravitational waves would be ancient, filling all of space uniformly, created in the first moments of existence, and they would leave a signature in the cosmic microwave background. When gravitational waves pass through space, they stretch and squeeze it in a particular pattern. This stretching and squeezing would affect the photons of the CMB as they traveled through space for 13.8 billion years. The effect shows up in the polarization of the CMB light. Polarization is the orientation of light waves. Unpolarized light vibrates in all directions. Polarized light vibrates preferentially in one direction. The CMB is slightly polarized. The scattering at recombination created a polarization pattern called E-modes, which we've detected and measured precisely. E modes are caused by density fluctuations, the sound waves in the primordial plasma. But gravitational waves create a different polarization pattern called B modes. These are like swirls or twists in the polarization across the sky, distinct from the patterns created by density fluctuations. B modes can only be created by gravitational waves or by gravitational lensing. The primordial B mode signal, the one created directly by inflation's gravitational waves, has never been detected. Multiple experiments are searching for it. Ground-based telescopes in Antarctica and Chile, high-altitude balloon experiments, proposed space missions. They're pushing the limits of detector sensitivity, trying to measure polarization differences of a few parts per billion. In 2014, the BICEP-2 experiment announced they'd detected B modes. The news was explosive. If confirmed, it would be direct evidence for inflation, proof that quantum gravitational waves were created in the first fraction of a second after the Big Bang. But further analysis showed the signal was contaminated by dust in our own galaxy. Tiny dust grains floating in the Milky Way can polarize light, creating false B-mode signals that mimic the primordial signature. The BICEP-2 detection was probably dust, not primordial gravitational waves. The search continues. Each year, experiments become more sensitive. Each year, they constrain the possible strength of primordial gravitational waves more tightly. The stakes are profound. B-mode detection would be direct evidence that quantum mechanics operates at the scale of the entire universe. It would confirm that the universe underwent exponential inflation. It would tell us the energy scale of inflation, how violent that expansion was. We're searching for the echo of the universe's first scream, the moment when space itself was born, stretching quantum whispers into cosmic roars. The moment when everything that exists was smaller than an atom, then suddenly, impossibly, became everything. That echo is still out there, still traveling, still waiting to be heard. We need to talk about where we are. Not on Earth, not in the solar system, not even in the Milky Way. We need to talk about our address in the cosmic web, our location in the vast structure of the universe. Because it turns out we live somewhere strange, somewhere unsettling, somewhere that might be biasing everything we think we know about the cosmos. We live in a void, not the vacuum of space. That's everywhere. We live in a cosmic void, a region of space where galaxy density is dramatically lower than average. A bubble of relative emptiness carved out of the cosmic web, surrounded by dense walls of galaxies, but internally sparse, quiet, hollow. This void is called the KBC void, named after the astronomers who identified it: Ryan Keenan, Amy Barger, and Lennox Cowie. It's enormous, about 2 billion light-years across, making it one of the largest voids ever discovered. And we're not on its edge, looking into it from the outside. We're inside it, deep inside it. The Milky Way, our home galaxy, sits roughly near the center of this cosmic hollow. Think about what this means. When you look out at the universe through telescopes, you're looking outward from the emptiest region in your cosmic neighborhood. The galaxy distribution you observe is not average. It's the view from inside a bubble where matter is scarce, where galaxies are fewer and farther between than they should be. Most astronomers assumed we lived in a typical region of the universe. Not special, not unusual, just an average patch of the cosmic web. This assumption is called the Copernican principle, the idea that we don't occupy a privileged position. Earth isn't the center of the solar system. The Sun isn't the center of the galaxy. The Milky Way isn't the center of the universe. We're typical, unremarkable, average. Except we're not. We're in a void. A region where the local expansion rate might be different from the cosmic average. A region where the flow of galaxies, the distribution of matter, The very fabric of space-time might behave differently than in denser regions. This discovery came gradually. Astronomers mapping the three-dimensional distribution of galaxies noticed something odd about our local neighborhood. Galaxy surveys showed we're surrounded by a region of lower-than-average density extending in all directions. But as surveys reached farther and mapped more galaxies, the picture became clearer. We really are in a void. Not a small one, not a marginal underdensity, but a genuine, massive cosmic void stretching billions of light years. This matters because it affects our measurements. When astronomers measure the expansion rate of the universe, they observe galaxies receding from us. But if we're in a void, the local expansion rate might differ from the global average. This could explain one of the biggest mysteries in modern cosmology, the Hubble tension. The Hubble constant should be constant. It's called a constant. It describes the rate at which the universe expands, how fast galaxies recede from each other per unit distance. Measure it anywhere in the universe, and you should get the same answer. Except we don't. There are two main ways to measure the Hubble constant. The first uses the cosmic microwave background. By analyzing the fluctuation patterns in the CMB and using our understanding of cosmology, we can calculate what the expansion rate should be today. This method gives a value of about 67 kilometers per second per megaparsec. The second method uses direct observations of the local universe. Astronomers measure distances to nearby galaxies using standard candles, objects with known intrinsic brightness. They measure redshifts to determine recession velocities. This method gives a value of about 73 kilometers per second per megaparsec. That's a 9% discrepancy. It doesn't sound like much, but in cosmology, it's enormous. Both methods are precise. Both have been refined over decades. The error bars don't overlap. One of them is wrong, or something fundamental is missing from our understanding. This is the Hubble tension, and it's one of the biggest crises in cosmology today. Could the KBC void explain it? Possibly. If we're in an underdense region, the local expansion rate could be higher than the cosmic average. Matter flows outward from voids toward the denser walls surrounding them. This creates a systematic effect where nearby galaxies appear to recede faster than they would in an average region. When we measure the Hubble constant using local observations, standard candles in galaxies within a few 100 million light-years, we're measuring the expansion rate inside the void. We're getting the local value, not the global value. But when we measure the Hubble constant using the CMB, we're measuring the expansion rate of the universe as a whole, averaged over the entire observable cosmos. We're getting the global value. If this is correct, both measurements are right. They're just measuring different things. The local expansion rate is genuinely higher than the global average because we happen to live in a void. This explanation is controversial. Not all cosmologists accept it. Some argue the void isn't large enough to explain the full discrepancy. Others point out that even if we're in a void, there are other voids in the universe, and observers in those voids should see similar tensions. But the idea is unsettling for a deeper reason. It violates the Copernican principle. It suggests we do occupy a special location, not at the center of the universe, but in an unusually empty region that biases our observations. It means that what we see when we look at the cosmos is not entirely representative of the universe as a whole. We're cosmologists trying to understand the entire universe, but we're doing it from inside a bubble, looking out through a distorting lens we didn't know was there. And there's something almost eerie about it. The realization that we've been observing the universe from the loneliest, emptiest place gravity ever carved. That our view of creation is the view from the void. Stand outside on a clear night, far from city lights. Look up at the Milky Way stretching across the sky. All those stars, all that light, all that cosmic grandeur. Now realize that you're looking at it from the middle of nowhere, from a cosmic desert, from the emptiest region for hundreds of millions of light years in any direction. The KBC void is not completely empty, of course. We're here. The Milky Way is here. The local group of galaxies is here. Andromeda, our nearest large galactic neighbor, is here. There are dozens of smaller galaxies in our immediate neighborhood. But compared to the cosmic average, we're in a remarkably sparse region. The average density of matter in the universe is about 1 proton per cubic meter. In the KBC void, the density is about 20% lower than that. It doesn't sound like much, but integrated over billions of light years, it represents an enormous deficit of matter. If you could somehow transport the Milky Way to an average region of the cosmic web, onto a filament or near a cluster, the night sky would look different. There would be more galaxies visible to the naked eye. More galaxy clusters within reach of our telescopes, more nearby neighbors in the cosmic web. Instead, we're isolated. We're in the cosmic equivalent of rural countryside, while most of the universe lives in cities connected by highways. This isolation might be a coincidence. Voids occupy about 60% of the universe's volume, so statistically, observers are more likely to find themselves in voids than in the dense walls and filaments. We might not be special, just statistically typical of observers in void-dominated universes. Or it might mean something deeper. Some cosmologists have speculated that void environments might be more favorable for life. Dense regions have more galaxy interactions, more supernova, more radiation, more catastrophic events that could sterilize planets. Voids are quieter, more stable, safer for long-term biological evolution. If this is true, then intelligent observers should expect to find themselves in voids, simply because voids are where intelligence is most likely to emerge and persist. We're not in a void by accident. We're in a void because that's where observers like us can exist. This is anthropic reasoning, and it's controversial. It explains our location by pointing to our existence, rather than deriving our existence from physical laws. Some scientists find this unsatisfying, almost circular, but it does give us perspective. When you look up at the CMB, when you think about those ancient photons passing through you, remember that you're observing them from inside a void. You're experiencing the afterglow of creation from one of the emptiest, loneliest vantage points in the universe. The ghost of the Big Bang surrounds you everywhere equally. But the view you have of that ghost, the particular pattern of galaxies and structure you see, is the view from the great hollow, from the quiet place, from the cosmic countryside where galaxies are sparse and the darkness between them runs deep. The cosmic microwave background isn't eternal. Neither is the universe we see today. Everything is changing, everything is fading, and the culprit is something we barely understand, something that makes up most of the universe's energy, something that's tearing the cosmos apart faster and faster with each passing moment. Dark energy. In 1998, two teams of astronomers studying distant supernovae made a discovery that shocked physics. They were trying to measure how much the universe's expansion was slowing down. Everyone expected gravity to be decelerating the expansion, gradually pulling everything back together. But the supernovae were dimmer than expected. They were farther away than they should be if expansion were slowing. The data pointed to only one conclusion. Expansion isn't slowing down. It's speeding up. The universe's expansion is accelerating. This makes no sense in normal physics. Gravity is attractive. Every form of matter and energy we knew about should slow expansion, not accelerate it. But something is pushing space apart, overcoming gravity, causing the expansion rate to increase with time. We call this something dark energy, though the name is a placeholder for our ignorance. We don't know what it is. We don't know where it comes from. We only know it exists because we can measure its effects. Dark energy makes up about 68% of the universe's total energy content. It dominates everything. And unlike matter, which becomes more dilute as space expands, dark energy maintains constant density. As the universe grows, the total amount of dark energy increases, making its effects stronger over time. This has devastating consequences for the future. Galaxies that aren't gravitationally bound together are being pushed apart by accelerating expansion. The Milky Way and Andromeda are bound. They'll eventually collide and merge in about 4 billion years. The local group, our collection of nearby galaxies, is bound. We'll stay together. But everything else is leaving. Galaxies beyond the local group are already receding from us, and they're receding faster and faster. Eventually, they'll be moving away so quickly that light leaving them will never reach us. Not because they're moving faster than light through space, but because space itself is expanding faster than light can cross it. These galaxies will cross our cosmic horizon. They'll redshift into invisibility. First, they'll fade as their light is stretched to longer wavelengths, shifting from visible to infrared to microwave to radio waves. Eventually, the wavelength will be stretched so much that detecting even a single photon would require waiting longer than the age of the universe. Within about 100 billion years, every galaxy beyond the local group will have crossed the horizon. An astronomer in that distant future, looking out at the universe with the most powerful telescope imaginable, will see only the merged remnant of our local group surrounded by absolute emptiness. No other galaxies, no cosmic web, no distant quasars, nothing but darkness extending infinitely in all directions. Let's think carefully about what this means for the cosmic microwave background. The CMB photons we detect today have been traveling for 13.8 billion years. They've been stretched by a factor of about 100 as space expanded. They started as visible light and became microwaves. But space is still expanding, and the expansion is still accelerating. The CMB photons passing through us right now will continue being stretched. Their wavelength will increase. Their energy will decrease. They'll shift from microwaves to longer wavelength radio waves. Eventually, they'll be stretched so much that they become undetectable. Think about what happens to a single CMB photon. It has a specific wavelength today, about 1.9 millimeters at the peak of the spectrum. In the future, as space continues expanding, that wavelength will double, then double again, then double again. The photons' energy decreases proportionally. As the wavelength stretches to centimeters, then meters, then kilometers, the photon's energy drops correspondingly. At some point, the photon becomes effectively impossible to detect. Its energy is so low, its wavelength so long, that no conceivable instrument could distinguish it from thermal noise or quantum vacuum fluctuations. The CMB doesn't disappear in the sense of ceasing to exist. The photons are still there, still traveling, still filling space uniformly. But they've been redshifted beyond detectability. They've faded into invisibility. Current estimates suggest this happens in roughly 100 billion years. If dark energy remains constant, then the CMB fades gradually but inexorably over this timescale. An astronomer 100 billion years from now, living in the merged local group galaxy, looking out at the universe, will see no CMB, no afterglow of the Big Bang, no evidence that the universe had a hot, dense beginning. They'll also see no distant galaxies. Everything beyond the local group will have redshifted beyond visibility or crossed the cosmic horizon. The observable universe will contain exactly one galaxy, their own, surrounded by empty space extending infinitely in all directions. From their perspective, the universe will appear eternal and unchanging. A single galaxy in an infinite void. They might conclude that their galaxy is the entire universe, that nothing else exists beyond the darkness surrounding them. They won't have the evidence we have. The CMB will be gone. The expanding universe will be invisible to them because everything observable will be gravitationally bound, not participating in the expansion. The cosmic web will be gone. All the discoveries we've made, all the evidence that pointed us toward understanding the universe's origin and evolution, will be unavailable to them. The universe will have hidden its own history, buried it under layers of expansion and redshift until it becomes unrecoverable. We live in a special time, a window of opportunity when the evidence of cosmic origins is still accessible. Before us, the universe was too young and too opaque. After us, it will have expanded too much. We're privileged observers living in the brief era when the cosmos reveals its secrets. But the story doesn't end with empty skies and faded light. The universe continues evolving, continues changing, continues dying. Star formation will eventually cease. Stars form from gas clouds, and gas supplies are finite. Each generation of stars locks some gas into stellar remnants, white dwarfs, neutron stars, black holes. Gradually, the available supply dwindles. In perhaps 1 trillion years, the last stars will form. After that, the universe will contain only the stars that already exist, slowly burning through their remaining fuel. The longest-lived stars are red dwarfs, tiny stars with masses perhaps 1/10 of the Sun's. They burn their fuel so slowly that they can shine for tens of trillions of years. They'll be the last lights in the universe, dim red embers gradually cooling as they exhaust their hydrogen. Eventually, around 100 trillion years from now, the last red dwarf will flicker out. The stelliferous era, the age of stars, will end. The universe will be dark. Not truly dark, perhaps. There will still be thermal radiation, infrared glow from cooling white dwarfs and planets. But no fusion, no stars, no new light being generated by nuclear reactions. The universe will enter what cosmologists call the degenerate era. It will contain only dead stellar remnants, planets, asteroids, and the ever-expanding darkness between them. Black holes will dot the void, slowly accreting stray matter that drifts too close. But even black holes aren't eternal. Stephen Hawking showed in the 1970s that black holes emit radiation, slowly losing mass through quantum effects near their event horizons. Eventually, over timescales that make trillions of years seem like seconds, even black holes will evaporate. A solar mass black hole takes about 10^67 years to evaporate. A supermassive black hole with 1 billion solar masses takes about 10^100 years. These numbers are incomprehensible. Writing out 10^100 in full requires a 1 followed by 100 zeros. The universe's current age is only about 10 to 10 years. The difference between these timescales is vast beyond any human conception. But time is infinite. Given enough time, even black holes evaporate. And when the last black hole finally evaporates, when its event horizon shrinks to nothing and its mass converts entirely to radiation, the universe will enter its final state. A thin mist of photons and fundamental particles spread across an ever-expanding space, growing more dilute with each passing eon. Temperature approaching absolute zero. Entropy approaching maximum. Nothing happens because nothing can happen. All useful energy has been exhausted. This is heat death, the ultimate fate of an accelerating universe. Not a dramatic ending, but a slow fade into darkness and stillness. The cosmic microwave background, that ancient ghost we've been tracing through this entire journey, will be part of that final mist. Its photons, stretched beyond recognition, will join all the other photons in the heat-death sea. The oldest light will become indistinguishable from everything else. A uniform, cold, eternal darkness. There's a line from Carl Sagan that has become almost cliché through repetition, but it remains true in ways most people don't fully appreciate. We are made of star stuff. But it goes deeper than that, much deeper. The hydrogen in your body. The hydrogen that makes up about 10% of your mass, that forms the backbone of every organic molecule, that flows through your blood as part of water, wasn't made in a star. It's older than stars. That hydrogen was forged in the first 3 minutes after the Big Bang, when the universe was still hot enough for nuclear fusion to occur everywhere at once. The protons in your body are 13.8 billion years old. They're the same age as the photons in the cosmic microwave background. They were created in the same primordial furnace during the same epoch of nuclear synthesis that created the light we've been discussing throughout this entire journey. You are made of the Big Bang. Not metaphorically, literally, the atoms in your body are survivors from the universe's first moments, forged when the cosmos was seconds old, preserved through billions of years of cosmic evolution, incorporated into stars and planets, and eventually into you. And the connection goes even deeper. Remember those quantum fluctuations during inflation? Those microscopic variations that were stretched to cosmic scales and became the seeds of all structure. Those fluctuations determined where galaxies would form, where the Milky Way would assemble, where our solar system would condense from a cloud of gas and dust, where Earth would form, where you would be born. The quantum uncertainty in a field that existed 13.8 billion years ago, when the universe was smaller than an atom, determined your location in space and time. A slightly different fluctuation pattern in the Milky Way might have formed somewhere else. Earth might not exist. You definitely wouldn't exist. Your existence traces back to the first fraction of a second after the Big Bang. You're not just made of the universe. You're a consequence of its structure, a product of its evolution, an inevitable result of the laws of physics playing out over cosmic time. And now, 13.8 billion years later, you're reading these words, thinking about the cosmic microwave background, understanding, however imperfectly, where you came from and what you're made of. This is extraordinary. Matter has become conscious. The universe has developed the ability to observe itself, to study itself, to understand itself. You are the universe looking at itself. When you observe the CMB, you're not separate from it. You're part of the same system. You and the CMB are both products of the Big Bang, both participants in cosmic evolution, both aspects of the same unfolding story. The universe began as pure energy. It cooled and formed particles. Particles formed atoms. Atoms formed stars. Stars forged heavy elements. Heavy elements formed planets. On at least one planet, chemistry became biology. Biology became complexity. Complexity became consciousness. And now, consciousness looks back at its origin. There's something almost miraculous about the fact that we can understand any of this. Think about what had to happen for you to be reading these words. The universe had to expand and cool at exactly the right rate. The fundamental constants, the strength of gravity, the mass of the electron, the speed of light, had to have precisely the values they do. If any were slightly different, stars wouldn't form, or they'd burn too quickly, or heavy elements wouldn't be synthesized. The CMB fluctuations had to have exactly the right amplitude. Too large and the universe would be dominated by black holes. Too small and no structure would form at all. 1 part in 100,000 was exactly right for producing a universe with stable stars and long-lived planets. Dark matter had to exist in exactly the right proportion to normal matter. Too much and structure would collapse too quickly. Too little and it would form too slowly. And then, after all of that, after 13.8 billion years of cosmic evolution, matter had to organize itself into a configuration complex, enough to be conscious, to think, to wonder, to develop language and mathematics and telescopes. Some call this the anthropic principle, the observation that the universe must have properties that allow observers to exist, because otherwise there would be no observers to notice. It's a tautology in some sense, but it's also deeply significant. It means we live in a universe that was, in some sense, ready for us. A universe whose properties allowed complexity to emerge. A universe where the laws of physics permit the existence of stable structures, complex enough to observe and understand those same laws. And we live in a special epoch. Too early and the universe would be too hot, too chaotic for complex structures to survive. Too late, and the universe will have expanded so much that evidence of its origin becomes undetectable. We exist in the window, the brief period, perhaps a few 100 billion years out of an infinite timeline, when the universe is cool enough for complexity, but hasn't yet expanded so much that its history becomes hidden. Future civilizations, if they exist, won't have access to the CMB. They won't see distant galaxies. They won't be able to reconstruct cosmic history the way we can. The universe will have hidden its secrets by then, erased the evidence through relentless expansion. We're the lucky ones. We get to see the afterglow while it's still visible. We get to observe the cosmic web while galaxies are still within view. We get to live in an era when the universe still remembers its youth, still carries evidence of its origin, and we do know how to listen. Through mathematics and physics, through telescopes and satellites, through human curiosity and determination. We've decoded the message, we've read the ancient light, we've understood the whisper. This is our privilege, this is our responsibility. To observe, to understand, to appreciate, to recognize that we're part of something vast and ancient and ongoing. To know that the photons passing through us right now are older than Earth, older than the Sun, older than the Milky Way itself. We are temporary configurations of atoms that have become aware of their own history. So here we are, at the end of this journey through the oldest light in existence. We started by asking you to notice the space between your hands, that apparently empty gap. And we've discovered that it's not empty at all. It's filled with photons from the moment the universe first became transparent. Ancient light, stretched and cooled by billions of years of expansion, still traveling, still present, still passing through every cubic centimeter of space. Right now, as you finish reading these words, roughly 400 CMB photons are passing through every cubic centimeter of your body every second. They've been moving at the speed of light for 13.8 billion years. They'll continue moving for billions more years, gradually stretching, gradually fading, but never stopping. You can't see them. Your eyes weren't built to detect microwaves, but they're there, as real as the screen you're looking at, as real as the air you're breathing. The cosmic microwave background is not a distant phenomenon. It's not something happening somewhere else. It's here, now, in this room, in your lungs, passing between the molecules of your skin. You are immersed in it, bathed in it, swimming through it at every moment of your existence. And you always have been. Every moment of your life, from your first breath to this exact second, You've been surrounded by this ancient light. It was there when you were born. It was there during every important moment of your life, every triumph and every tragedy. Silent, invisible, ancient, eternal. The ghost in the room. The presence that's always with you, has always been with you, will always be with you. This is the nature of the universe we inhabit. Not empty space dotted with isolated objects, but a connected medium where everything influences everything else, where the past is still present, where light from the birth of time still surrounds us. You are not separate from the cosmos. You're part of it, made of it, connected to it in ways both physical and profound. The hydrogen in your body remembers the Big Bang. The atoms in your bones were forged in stars. The pattern of galaxies in the sky was determined by quantum fluctuations that happened when the universe was smaller than a proton. Everything is connected. Everything is part of the same story. And that story is still being told, still unfolding, still evolving toward an unknown future. If this journey through the oldest light in existence brought you a moment of wonder, a sense of connection to something vast and ancient, a glimpse of the profound strangeness of reality, then a gentle like or subscribe to Space Doze would mean everything. It tells me you're out there drifting through these cosmic mysteries with me. Sleep well, Stardust. The ancient light is still with you, and it always will be. Good night.